System calls. The interface between applications and the operating system. In this video, we'll be exploring what system calls are and why they're such a crucial component in operating systems. System calls provide the essential bridge between user applications and the operating system kernel. System calls are programmatic interfaces that allow user-level applications to request services from the operating system kernel. They serve as the gateway between user space and kernel space, providing controlled access to hardware resources and protected operations. For example, consider opening a file in C. Here's the code. Include fcntl.h, include unis.h. Int main, int fd, open is a system call, fd equals openfile.txt, o_rd only. Return 0. There are several types of system calls, including file management, process control, device management, information maintenance, communication, and protection. File management system calls handle file operations such as creating, opening, reading, writing, and closing files. Examples include open, close, read, write, seek, and unlink. Process control system calls manage processes, including creation, termination, and synchronization of processes. Examples include fork, exec, exit, wait, kill, and sleep. Device management system calls interact with devices, handling input-output operations and device allocation. Examples include iactl, read, write, map, and select. Information maintenance system calls transfer information between user programs and the operating system. Examples include getpid, getchouit, time, date, chmod, and chown. Communication system calls create and manage communication channels between processes. Examples include pipe, socket, connect, accept, send, and receive. Protection system calls control access to resources and implement security mechanisms. Examples include chmod, chown, setchouit, getchouit, umask, and access. Here's how system calls work. First, the application program invokes a system call through a library function. The library sets up the system call number and arguments in registers. Then, a trap instruction triggers a mode switch from user to kernel mode. The kernel executes the system call handler based on the system call number. Finally, the kernel returns the result to user space and switches back to user mode. Consider the diagram. In user space, we have the application and the C library. The application makes a call to the C library, which in turn uses the system call interface to request services from the kernel space. In kernel space, the system call handler processes the request and returns the results back to user space. The mode switch happens between the user space and kernel space. Let's explore the system call mechanism with a C code example. Include fcntl.h, include unis.h, int main, int fd, char buffer of 100, fd equals opendata.txt, o_rd only. Read fd buffer 100, close fd, return 0. When a program calls open, read, or close, 1. The C library function prepares arguments and places the system call number in a register. 2. A special instruction, for example syscall svc, or in 0x80, triggers the CPU to switch to kernel mode. 3. The kernel system call handler validates the arguments and permissions. 4. The kernel executes the requested operation with privileged access. 5. Results are returned to user space, and execution continues in user mode. There are several methods for passing parameters to the kernel, including registers, memory blocks, and the stack. Registers. Parameters are passed through CPU registers, which the kernel can access directly. Pros include fast access and no memory copying. Cons include a limited number and size constraints. Memory blocks. Parameters are stored in a block of memory, and a pointer to this block is passed via register. Pros include handling many parameters and supporting large data. Cons include memory overhead and potential security risks. Stack. Parameters are pushed onto the user stack, and the kernel accesses them from there. Pros include simple implementation and a familiar mechanism. Cons include the need for stack validation and the potential for stack overflow. Operating systems provide different API levels for accessing system calls. Native system calls, direct kernel interface, typically accessed through assembly instructions. See standard library libc. Wrapper functions that simplify system call usage. POSIX API, standardized interface for Unix-like systems. Win32 API, Windows System Call Interface. Higher-level libraries, language-specific abstractions, for example, Java JNI, Python OS module. Most applications use higher-level APIs rather than invoking system calls directly. For example, low-level system call Linux x86_64, long syscall long number ... See library wrapper. An open const char pointer path name int flags. POSIX compliant wrapper. An open const char pointer path int offlog ... Windows API equivalent. Handle create file, lpcstr filename, dword do desired access, dword do share mode, security _attributes security attributes, dword do creation disposition, dword do flag sand attributes, handle template file. Here's the system call flow. First, the user process initiates a system call. This call goes through the system call interface to the system call handler. The kernel then performs parameter validation, checks permissions, and executes the kernel service. Finally, the results are returned to user mode. The CPU switches from user mode to kernel mode, preserving the user context to allow returning to the same state. The kernel validates all parameters passed from user space to prevent security vulnerabilities and system crashes. The kernel verifies that the calling process has appropriate permissions to perform the requested operation. System calls are typically implemented using a dispatch table that maps system call numbers to their handler functions. System calls introduce significant overhead compared to regular function calls due to several factors: mode switching, transitioning between user mode and kernel mode; context saving, saving and restoring CPU registers in state; parameter validation, checking arguments for validity and security; memory copying, moving data between user and kernel space; cache effects, potential cache flushes during mode transitions. In terms of optimization techniques, you can use batching, combining multiple operations into a single system call to reduce the number of mode switches. Asynchronous input-output, initiating input-output operations without waiting for completion, allowing the process to continue execution. Memory mapping, using shared memory regions between user and kernel space to avoid copying data. System call reduction, designing applications to minimize the frequency of system calls through caching and buffering. Modern operating systems continue to evolve with new mechanisms like virtual dynamic shared object and syscall instructions to reduce system call overhead. Key takeaways. System calls form the essential boundary between user applications and the privileged kernel, providing controlled access to hardware and protected operations. They enforce security by validating parameters, checking permissions, and preventing direct access to critical resources from untrusted user code. System calls provide hardware abstraction, allowing applications to be written without knowledge of specific hardware details. Different operating systems implement system calls differently, but all involve a controlled transition between user and kernel modes. System calls have significant overhead compared to regular function calls, requiring careful design to optimize application performance. Most applications use higher-level APIs that abstract the underlying system calls, improving portability and ease of development. System calls are the foundation of operating system design, enabling the secure and controlled interaction between user applications and the privileged kernel. Understanding system calls is essential for developing efficient, secure, and portable software. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.